Bom, boa tarde. Temos prazer de ter hoje o professor Pierre Descouvemont, da Universidade Libre de Bruxelas, para falar aqui. O professor Pierre, ele faz parte como colaborador do nosso grupo de Astrofísica nuclear do Instituto de Estudos Avançados, e ele está passando aqui na USP como visitante do Instituto de Estudos Avançados e também do Instituto de Física. Está passando alguns meses colaborando com algumas pessoas, inclusive a professora Alinka, eu, o professor, enfim, outros professores aqui na USP. E o professor Pierre recebeu o mestrado em engenharia na Universidade Libre de Bruxelas, em 81. Em 86, ele obteve o doutorado em física nuclear na mesma universidade, fez a sua livre docência na Astrofísica nuclear em 89. Depois, ele atualmente trabalha em física nuclear e astrofísica nuclear teórica e já publicou mais que 200 artigos científicos na área. Atualmente, ele é diretor de pesquisa na FNRS, da Bélgica, e chefe do Departamento de Física Nuclear e Teoria Quântica de Colisões na Universidade Libre de Bruxelas. E hoje ele falará sobre onde está? Sobre Nuclear Astrophysics from Stars to Nuclei. Professor Pierre.
Okay, thank you very much for the introduction. So I'm going to talk about nuclear astrophysics, which is a combination of astrophysics and of nuclear physics. And as you know, astrophysics is trying to study stellar evolution, and this is a field which requires many inputs from thermodynamics, from plasma physics, from atomic physics, and also from nuclear physics. And this is a field which is called nuclear astrophysics, and this is what I'm going to talk about today. And in the first part of my talk, I will briefly describe you some astrophysics scenario, and then I will come to the nuclear physics point of view and to show you how important is nuclear physics in astrophysics. And as my talk will be a kind of journey between very large scale and very small scale, I'd like first to discuss a little typical dimensions. So the biggest object that we can think of is a galaxy, and you have here our galaxy, which is quite large. So the typical dimension of the galaxy is about 10 to the 21 meter. You have here this star, which represents our sun. And you have here at the other extreme the very small scale, which is the nucleus. And what I'm going to show you is the relationship between these two extremes. One is sorry, there is okay. So one is the nucleosynthesis, where nuclei are formed by the stars, and the other, it also goes in the other direction. So nuclei are used by the stars to produce the energy. So here you have the typical dimensions. So the typical dimension of the galaxy is about 10 to the 21 meter. This is of course, very large. And the atomic nucleus is a tiny dimension, which is about 10 to the 15 Fermis, 10 to the 15 meters, which corresponds to about 1 Fermi. And of course, the typical masses are here. You have about 10 to the 42 kilo for the galaxy, which represents about 10 to the 12 solar masses, and the mass of the nucleus of about 10 to the 26. So we have here two extremes, very large scale, very small scale, and because it's difficult to imagine, I'd like to show you some intermediate steps, some typical dimensions. So the largest one is the galaxy with 10 to the 21. So if you consider a star like the Sun, it's about 10 to the 9 meter. So you have 12 orders of magnitude smaller. And then you have the Earth, which is about 6,000 kilometers radius. And then if you go lower in size, you have a football ball, which is, well, smaller than 1 meter, but we are talking about a logarithmic scale, so 1 meter is a good approximation. And then if you go to lower dimension, then you have you have the atom here. And the typical dimensions are the angstrom, so 10 to the minus 10 meters. So these are the different typical examples between the two extremes. And well, it's amazing to see that the football ball is almost exactly in the middle of the largest and of the smaller size. So let's discuss about the density. If you compare the size and the mass of the nucleus of the atom, so you have the atom on the left side. The atom is almost empty. It's made of the nucleus, the protons and neutrons here, and of the electrons. But the mass of the system is essentially given by the masses of the neutrons and protons, because the electron mass is very small compared to the nucleon mass. And now, if you look at the nucleus, the size is about 100,000 times smaller, but the mass is about the same, because here you have protons and neutrons. So because the volume is proportional to the size to the power 3, so, and there is a factor 10 to the 5 with the size of, in comparison the size of the atoms and of the nucleus, the volume is different by a factor 10 to the power 15. So it means that the densities are very different and are different by a factor 10 to the power 15. So the nuclear density is very large and much larger than the atomic density. And well, it's difficult to imagine that at the human scale. So I have here a small comparison. So if you use standard density, which corresponds to water or to our human body, it's about 1 gram per cubic centimeter. So now, if you consider nuclear density, the nuclear density is 10 to the 15 times this standard density. So 1 cubic centimeter of nuclear density would correspond to 1 billion tons. And to understand, to have another comparison, you can compute the total weights of all human beings on Earth. So if you consider that there are about 6 billion inhabitants on Earth, and if you assume average weight of 70 kilo per inhabitant, you can change the weight per inhabitant. It doesn't change the conclusion. So if you multiply the number of inhabitants by the weight, you find total mass of 4 to the 10 to the power 14. And now if you compare this number with the nuclear density, so it means that if you were made of nuclear density, all human beings on Earth would fit in about 0.5 cubic centimeter. So the nuclear density is very high, and we may wonder whether it's pure game for a nuclear physicist or if it's does exist. And in fact, this nuclear density exists in some stars, which are called neutron stars. So you have here a picture of a neutron star, which is the remnant of a supernova explosion, and essentially contains neutrons. And the typical diameter of a neutron star is about 10 to 20 kilometers, which is nothing compared to the diameter of a normal star. You have here the diameter of the Sun, which is about 1 million kilometers. So these neutron stars are characterized by the nuclear density. And also we can reproduce this nuclear density in the laboratory with what is called quark-gluon plasma. So you imagine two heavy nuclei colliding at very high energy. And of course, for a very short time and in a very limited region of space, you have the formation of nuclear matter. So this nuclear density can be reproduced in the lab. Okay, with this small introduction about typical nuclear densities, then I'm coming to the main part of my talk, which is about nuclear astrophysics. So the main questions that astrophysicists want to answer is how stars are born, how do they evolve, and how do they die. This is the main idea of stellar physics. And I'm going to show you with a very brief summary of the life of a star. And we know that universe has been created by the Big Bang. And then soon after the Big Bang, nuclei have been created when temperature was low enough to make sure that nuclei exist. And then what is formed by the Big Bang are called interstellar clouds, where you have essentially hydrogen and helium. These two elements are produced by the Big Bang. And then in some region with higher density, you may have what is called gravitational contraction. And after some time, this leads to the formation of a star. And then the main part in the life of a star is called nucleosynthesis. So this is represented by this red arrow here. And this is where nuclear physics is very important. There are many reactions which are important, and I will talk about that in a moment. And then at the end of the life of a star, if the star is massive enough, then you may have a supernova explosion, which is the end of the star. And you have here a diagram of that. And then all elements which have been produced by the nucleosynthesis are reintroduced in the interstellar clouds. So one of the roles of the stars is to build new elements by the nucleosynthesis and to expand them in the interstellar clouds. So this is a very general picture of star evolution. Now I'm going to briefly describe each of these parts. So, but before that, I just want to show you an important diagram, which is the mass fraction of the different elements at different stages. So you have here the mass fraction as a function of the nuclear mass, which here in abscissa. These are snapshots at different times. So this is the first one here. It's just after the Big Bang. So you have essentially hydrogen and helium. And you have very small parts of lithium, beryllium, and carbon. But essentially hydrogen and helium, and there is nothing else. And these are very old stars. So after the nucleosynthesis, some other elements are produced. So this is on this diagram this diagram, which is here. And then if the star is more recent, you have another diagram here. So if the star is more recent, it means that it has been formed from a molecular cloud which contains a few other elements. So this is why, in this case, you have heavier elements here that you can see, and this is the abundance in the sun as it is today. So essentially, the main elements are still hydrogen and helium, so mass 1 and mass 4, but you can see that you have many other elements. So this is a clear indication that stars produce new elements, because after the Big Bang there is nothing, and now in the sun you can see the production of many other elements. So let me start with the Big Bang, which was initiated by Georges Lemaitre, which was Belgian. He was at the same time priest and cosmologist. So he suggested that the universe was created from a very hot and dense state, and that it produces essentially hydrogen and helium. And well, there are several evidences for the Big Bang. One is the cosmic background. So the universe behaves as a black body with a temperature of 2.9 Kelvin. So this is now well established. And other evidence for the Big Bang is the expansion of the universe. So if you look at two different galaxies, the velocity is proportional to the distance. So it means that all galaxies are moving away from each other. And if you go backwards in times, so if you go to time 0, it means that you have a very dense and very hot sphere at the beginning. And this is known as the Hubble law, which says that the velocity is proportional to the distance, and the Hubble constant is now known with rather high precision, and from the Hubble constant you can deduce the age of the universe, which is about 13 billion years. And now I keep my small summary here of the star evolution. Now let's talk about formation of stars. So after the Big Bang, there is the formation of molecular clouds, and at some parts of these molecular clouds there may be gravitational contraction which provides you with a star. And I have here a simulation. So this is a numerical simulation showing the formation of stars from a molecular cloud. The black parts correspond to the low density regions, and the yellow and white corresponds to the high density regions. So you can see that there is formation of different high density regions which corresponds to stars. And well, the time scale of this event is between 100,000 and 10 to the 7 years, which in fact is very short at the time scale of the universe, which is about 13 billion years. So at the end of the process, you have the formation of high density regions which corresponds to stars. Okay. Okay, so now let me talk about nucleosynthesis, which is the main issue in nuclear astrophysics. And here we know that nuclear physics plays a very important role. So let me begin with a very important property of the nucleus, which is the binding energy. So on this diagram, you have the binding energy per nucleon. So it's the total binding energy B divided by the nucleon number. And this is plotted as a function of the mass number, so the total number of nucleons. And as you can see, there are here two regions which are separated by this vertical line, which corresponds to iron. The most bound nucleus is iron 56. And, well, if you go on the right side of this iron 56, you have heavy nuclei. And in this region, if you break a nucleus, then the products are more bound, that the sum of the binding energies are larger than the initial binding energy. So this is the idea of fission. This is how nuclear reactors work. But now if you look at the left side, which is in this region, which corresponds to the one which we are interested in nuclear astrophysics. Here you gain energy by increasing the number of nucleons. So if you add a proton or an alpha particle, you end up with a nucleus which is more bound. And this is how stars produce energy. And this is also the idea to produce energy by fusion. And you know, this is a very old idea to reproduce what happens in stars. And there is a recent project which is called ITER. And this is located in the south of France, in this white county called Cadarache. They try to produce energy exactly in the same way as stars do, by fusion. And here the reaction is deuterium plus tritium, which releases an energy of 17 MeV. And here the temperature is very high, and the region is that nuclei are positively charged. So there is a repulsion due to the Coulomb barrier, and I will come back to that later. And to overcome this repulsion, you need to use very high temperature. The sun is the core of the sun is about 15 million degrees, and temperature in ITER is 10 times larger. And of course, the main problem in this situation is to produce more energy than you consume, otherwise it's useless. And this is the main problem. So it's now clear that the energy production in the nuclear and the nucleosynthesis comes from nuclear reactions. And this was suggested by Gamow and Bates almost 1 century ago. So after the discovery of the nucleus by Rutherford and after the first nuclear reactions, Gamow and Bates suggested that the nucleosynthesis in stars comes from nuclear reaction. And then a very important paper was published by Burbidge, his wife, Burbidge, Fowler, and Hall. And this is a very famous paper in nuclear astrophysics. It's referred to as B2FH. And in this paper, which is entitled Synthesis of the Elements in Stars, they classified reactions by cycles. So they go further than Gamow and Bethe. They classified reactions and explain how nucleosynthesis may occur. And Bethe and Fowler were awarded by the Nobel Prize in 57 and 84. So we know that nuclear reactions in stars are performed by various processes. And the most important one, are, at least for light elements, are hydrogen burning and helium burning. So I will talk about that in more detail. And for heavy elements, nuclei are produced by neutron captures. This is what with the so-called S and R processes, but I will not talk about that today. And well, to to understand the reactions in nuclear astrophysics, you have to go back to the different forces which exist in the nature, because there are different reactions which arise from different forces. So the amplitudes are expected to be very different. We know that in the nature there are 4 forces. One is the nuclear or strong interaction, and the amplitude is chosen as the reference. Electromagnetic interaction has an amplitude which is given by the fine structure constant, 1/137. Then there is the weak interaction, which is important in the beta decay, which has a very small amplitude, 10 to the minus 5. And of course, there is also gravitation, but the gravitation doesn't play any role in the nucleosynthesis. And the reactions can be classified in 3 different types. You have transfer reactions, and in transfer reactions, you have nucleons which are transferred from one nucleus to another one, and this arises from the strong interaction. You may have radiative capture reaction, which are shown here. Then you have 2 colliding nuclei, and the residual nucleus emits a photon, which has some energy, and this energy is released by the reaction. And the radiative capture reaction comes from the electromagnetic interaction. So you may expect an important difference between transfer and radiative capture reactions. So the probability of the reaction, which in nuclear physics is referred to as cross-section, it strongly decreases. And there is one important reaction of weak capture. This is the PP reaction. And this arises from the weak interaction. And of course, the probability is very small, but this is the only way to produce heavier elements than protons. So this is a very important reaction. And well, this is a reaction which determines the lifetime of the star. And well, there is no possible transfer. When you have 2 protons, you cannot have transfer. You may have radiative capture, but diproton does not exist. It's not bound. Because when you have 2 protons, they attract each other by the nuclear force, but they repulse each other by the Coulomb force. And the Coulomb force is more important. So diproton does not exist. So the only way is to have the weak capture. And this has a very low probability, and it's impossible to measure, but they are very accurate calculations. And it's very interesting to make a very small exercise, is to assume that diproton is bound. Diproton is unbound by a very small energy. So if you assume that it's bound, then radiative capture would be possible. And then the cross-section, so the probability for the reaction to occur would be multiplied by about 10 to the power 6. So this comes from the ratio between the weak interaction and the electromagnetic interaction. So the hydrogen would burn 10 to the 6 times faster. It's like in your car, if you consume more, then you have to refill the tank more often. So if the diproton would be bound, then the lifetime of the sun would be smaller by the same factor, about 10 to the 6. So instead of having 10 billion years, the sun would burn hydrogen only during 10,000 years, which is nothing compared to the lifetime of the sun. So the first part of nucleosynthesis is hydrogen burning. So you have protons, and you have to produce heliums from these protons. And there are 2 different ways to produce helium from hydrogen. One is the PP chain, and the other one is the CNO cycle. And the PP chain is represented here. So you start from 4 protons, and then 2 pairs of protons interact by this PP reaction to produce deuteron. And then the deuteron may capture an additional proton, and you have this deuteron P gamma reaction. So you are left with 2 helium-6, and then the final reaction is the last one here, helium-3 plus helium-3, giving alpha plus 2 protons. And the final energy released by the PP chain is 27 MeV. So the whole of the PP chain is to produce energy and to produce helium from proton. And there is another way to convert proton in helium, which is the CNO cycle. So if the star is young enough, when it was created, it may contain a very small amount of carbon-12. And this carbon-12 may act as a catalyzer, and as I will show you here. So if you have carbon, the first reaction is the carbon-12 P-gamma reaction, which provides nitrogen 13. It's a P-gamma reaction. And then nitrogen 13 is radioactive, so it decays by beta emission to provide carbon 13. And then carbon 13 captures an additional proton, this carbon 13 P-gamma. Nitrogen 14 is stable, so it may capture an additional proton, and you have nitrogen 14 P-gamma reaction, which produces oxygen 15. But oxygen 15 is unstable, so it decays to nitrogen 15. And nitrogen 15 may capture an additional proton. And then you have nitrogen 15 P gamma and nitrogen 15 P alpha. But P alpha is a strong reaction with a larger cross-section. So P gamma is completely negligible. So at the end, you end up with your carbon-12, the initial carbon-12, and helium. So you have this cycle which is presented here. The same helium is produced by 4 protons, but in a different way with carbon-12 as a catalyzer. Okay, so when hydrogen is exhausted, then starts helium burning. And here, if you take 2 alpha particles, they cannot produce heavier elements. So 2 alpha particles can only have elastic scattering. So they ignore each other. They don't produce heavier elements. Beryllium-8 is unstable. So alpha plus alpha capture is not possible. So the mechanism to produce heavier elements from alpha particles is the triple alpha processes, where you have 2 alphas which are in equilibrium with beryllium-8, and then captures the further alpha particle. So this is the first step of the helium burning, which is the triple alpha process. The next step is C12 alpha gamma. And this reaction is very important in nuclear astrophysics. But it's extremely important, but also extremely difficult. And there are many people who have been working on C12 alpha gamma. And the next reaction is oxygen 18 alpha gamma, and so on. And the triple alpha process is a very nice example of the importance of nuclear physics in astrophysics. We have here, you have here on the left side the spectrum of carbon-12, and the threshold of alpha beryllium-8 is here, 7.36. And it was known for a long time that carbon-12 is very abundant in the universe. So this large abundance could only be explained if a resonance was present in the carbon-12 spectrum. And this resonance is the one here, 0 plus resonance, just above the threshold. This was predicted by Hall in 1954, and it was found experimentally later. So this is a nice example of the importance of nuclear astrophysics. A nuclear state was predicted from observational abundances. Okay, so now let me come to the final stage of star evolution. So this is the final stage here. So in normal conditions, there is an equilibrium between the gravitational force, which is attractive, and the radiation force produced by nucleosynthesis, which is repulsive. So the stars is in equilibrium. But there is no more hydrogen, helium, and so on. When the fuel of the star is exhausted, then the core contracts, and you may have, if the star is massive enough, you may have explosion, which is a supernova event, and this is shown in this, should be shown in this movie. No. Okay. So we can imagine explosion of a supernova, and this is a very short event. So the typical time scale is a few months. So which at the scale of star evolution is very short, and these supernova events ejects many elements in the interstellar medium. So here the elements which have been produced by the star are re-injected in the molecular clouds. And this type of events involve many nuclear reactions. So there are many nuclear cross-sections that you should know. So the whole of nuclear reactions can be summarized by two main issues. One is to produce the energy released by the star, and the other one is to produce a nucleosynthesis. And this figure here is very important in astrophysics. So this shows the abundance of the elements. This is for the galaxy as a function of the mass of the elements. And from this diagram, which comes from observation, you can deduce many nuclear properties. One of these properties is that if you look in the low mass region here, you see that there is a gap between mass 4 and mass 12. And this is explained by nuclear properties. There is no stable nuclei for A equal 5 and A equal 8. So if you have alpha and a proton, they cannot make lithium-5 because lithium-5 does not exist. And another effect that you can see is that there are maxima. And these maxima are explained by nuclear physics. They correspond to magic numbers, which correspond to nuclei which are more bound. So if the binding energy is large, these elements are more difficult to destroy, and so you can see that they are more abundant. These are these peaks here. And you can also see that there is an even-odd effect. So the red points correspond to even nuclei, and the blue point corresponds to odd nuclei. And you see that even nuclei are more abundant. And this is also explained by nuclear physics. We know that even nuclei are more bound, and again, they are more difficult to destroy than odd nuclei. Okay, so this was a brief summary of the needs for nuclear astrophysics. Now let me discuss nuclear physics properties and how to determine this cross-section. This is another important figure in nuclear physics. This is the chart of the elements. So each dot here corresponds to one nucleus. You have in horizontal axis the neutron number n, and here the proton number z. And the black points correspond to stable nuclei. And you see that if you are in the light mass region, stable nuclei correspond to n equals z. But then when the mass increases, because of the Coulomb repulsion, you need more and more neutrons to stabilize the nucleus. And this is why there is a curvature here. So this is not anymore a straight line. And if you go on the left side or on the right side of this line, you have the neutron-rich in this region here, or the proton-rich element on the left side of the stability line. And to show you how important is this field, you have here a figure which I took from a very recent paper. This is the number of known nuclei as a function of year. You see here the stable nuclei, which is the red curve. And well, it's called near stable because if the nuclei have a very long lifetime, million years or so, they are considered as stable. And you see here these green curves and blue curves corresponds to proton-rich and neutron-rich elements. So if you see the total of number of known nuclei is given by this black curve. And if you look at the last 20 years, so after 1990, about 500 new nuclei have been found experimentally. So this is a very important work. And for astrophysics, at least for hydrogen and helium burning, we are essentially dealing with this low mass region. In this high mass region, nuclei are produced by neutron capture, S process and air processes. And I will focus essentially on low mass region. So the reactions which are important for astrophysics are essentially P gamma, alpha gamma, and P alpha reactions. So these are reactions which are involving charged particles. So because the lifetime of the neutron is about 15 minutes, so there is no more neutron, only protons and helium. And an important quantity considering reactions is the probability of reaction, which is called the cross-section. And the dimension of a cross-section is a surface. Typical units are bars, which corresponds to 10 to the minus 28 square meter. And this cross-section strongly depends on energy. And the interaction between two particles can be represented by a potential. So you have here in this diagram a typical potential between two particles. So R here is the distance between the two particles. And you have two components. One, which is the nuclear force. And we don't know exactly what the nuclear force is, but we know that it's attractive and that it's at short distances. So you can see here after a few Fermis, it's almost zero. And the other component is the Coulomb interaction, that we know the Coulomb interaction and it's repulsive. So if you make the total here, you have this red curve here, which is the total of the nuclear and Coulomb interaction. And if you look at a zoom, so if you make a zoom on this region here, you have this picture where you have here an important quantity for reaction, which is the height of the Coulomb barrier, VB. This is very typical energy for reactions. And as I will show you in a moment, the typical energies in nuclear astrophysics are very low compared to the Coulomb barrier. So it means that they are dominated by Coulomb effect, by repulsive Coulomb effect. And one of the main problems in nuclear astrophysics is that the cross sections are very small because of this repulsion. So the typical energy for astrophysics is given by this arrow here. And in classical mechanism, the reaction would be impossible because in classical mechanic, the total energy must be larger than the potential energy. But there is quantum mechanics and there is Tunnel effect which allows the reaction to occur. And because this reaction proceeds at very low energy, then the cross-section is essentially given by a Coulomb factor. And the Coulomb factor is given here, where eta is called the Sommerfeld parameter, and is proportional to 1 of the square root of the energy. So if the energy goes to low values, then eta is large, so Coulomb effects are large, and this factor is very small. And you have here a plot of this factor, exponential minus 2 pi eta as a function of energy. This is a logarithmic scale. And as you can see, and as expected, it goes to very low values at low energies. And this is the reason why the tradition in nuclear astrophysics is not to use a cross-section, but the S factor, which is defined here. Well, you can see in the bottom of the slides. So the S factor removes this main Coulomb effect and is in a smooth dependence on energy. You can see here an example, which is the helium-3 alpha gamma cross-section. And as we expect from the Coulomb dependence, the cross-section goes to very low values here. And if you convert this cross-section into the S factor, then you have something which is almost constant with energy. So this is a logarithmic scale. The cross-section is presented here in logarithmic scale, and the S factor in a linear scale. And the arrow, these red arrows here show a typical domain for nuclear astrophysics. So typical astrophysical energies are very close to zero. And well, this was for an example of helium-3 alpha gamma, which is a typical non-resonant reaction. And in some cases, you may have resonances which are superimposed to the non-resonant part, which is also called direct capture. And then you have to know the properties of these resonances, energies, widths, and other quantities. And well, in fact, to explain the origin of the low energies, you have to go back to the reaction rate. So the reaction rate is the important quantity in stellar models. And the reaction rate is defined from the cross-section, but it's an average of the cross-section times the distribution, the energy distribution inside the star. And in most cases, the distribution is assumed to be a Maxwell-Boltzmann distribution, which is something very well known, which decreases exponentially with energy. So to compute this integral, you have the product of two terms which are presented here. One is the blue curve is the cross-section, and we have shown before it's increased very fast with energy. The other part is this red curve here, which corresponds to the Maxwell-Boltzmann distribution. And if you make the product, so this is what you need to compute the reaction rate here. You have this green curve, which present a maximum, which is even better seen in a linear scale. And so you have here a maximum which is called a Gamow peak. And in all cases, E0, which is the Gamow energy, is much smaller than the Coulomb barrier. So you are at very low energies and you have very low cross-section. And you have here some typical examples for some reactions, DP, helium-3, alpha plus carbon and carbon plus carbon. These are typical temperatures. 15 million degrees correspond to the center of the sun. 200 million degrees corresponds to helium burning. And you see that the E0 here, so this is the energy where you have to know the cross-section, is always much smaller than the Coulomb barrier. So the cross-section in astrophysics are almost small. And this is somewhat contradictory with the naive picture or the intuition of the star when the temperatures are very large and energy is very large. And of course, this is true at the human scale. So temperature is very large, but at the nuclear scale, temperature is something which is not large. So what you end up with is that these energies here below the Coulomb barrier corresponds to the low energy region and to the low cross-section region. So in most cases, experiment cannot go to stellar energies. So here there is a need for calculations and for extrapolation of the experimental data. So there are essentially two challenges for experiments. One is, as I just said before, low cross-sections. So to deal with the low cross-section, one way is to reduce the background. And to reduce the background, possibility is to go underground. And you have here one example, which is Luna in Gran Sasso. So Gran Sasso is a mountain in Italy. There is a tunnel. And inside the tunnel, there is a laboratory with several experiments on neutrinos, on dark matter. And there is one which is called Luna, a laboratory underground for nuclear physics. And there they can go to very low energies. And for one reaction, they could reach the Gamow range. Another way to deal with this low cross-section is to use indirect methods. And there are different indirect methods, and I just want to mention one, which is Coulomb dissociation. What you are interested in nuclear astrophysics is this reaction here, the fusion reaction where you have A plus B giving C plus gamma. And a possibility is to use the reverse reaction. So instead of you looking at the capture reaction, you look at this breakup reaction, which is the reverse of the capture reaction. And then you end up with larger cross-sections, which is nice. And you know that there are reverse reactions. So with the balance detail theorem, you can go from one cross-section to the other one. The only problem is that you can only produce beams in the ground state. So you can only access the ground state cross-section. And if there are excited states, you cannot deal that with indirect methods. Another important challenge for experiments is the need for radioactive beams. And again, I'm coming back to this chart of the elements, where you have these blue dots here, which corresponds to stable isotopes. And you have here many isotopes in yellow here, neutron-rich or proton-rich, which have finite lifetime. And the lifetime can be of the order of the millisecond, or the second, minutes, and so on. And there are many stellar processes which involve radioactive nuclei. And then you cannot make a target with a radioactive nucleus because it would disappear in seconds or in minutes. So the only way to measure this cross-section is to use a radioactive beam. You have here some example, lithium-8, nitrogen-13, fluorine 18. Nitrogen-13 was the first beam, which was the first radioactive beam, which was produced in Louvain-la-Neuve in almost 20 years ago. It was the first radioactive beam in the world. Now there are many radioactive facilities, and one which is very close to here is the RIBRAS facility, which is installed at the Pelletron laboratory. Probably all of you know. And the main difficulties which are associated with radioactive beams, and they are not specific to RIBRAS, they are common to all radioactive facilities, is that there are low intensities, because these radioactive beams must be produced a reaction. So the beams have low intensities compared to stable beams. And another problem is that they are contaminants, so the beam is not pure, and they must be removed from the data. And so there are also challenges for theory. The nice thing of theory is that you don't care about the radioactive character of a nucleus. Radioactive and stable nuclei can be equally treated, and you can also deal with very low energies. But of course, you have to describe the reaction mechanism with good accuracy, and you also need a good description of the resonances. So this is why you need nuclear spectroscopy. And well, nuclear astrophysics is a field where there are many challenges, and this is a list of challenges which are common to experiment and theory. So one of the problems is that stellar models require many reaction rates. Of course, there are some reactions which are very important, like C12 alpha gamma or beryllium 7p gamma. But if you want to be accurate, at least astrophysicists use sometimes up to several thousands of reaction rates. So you cannot be satisfied with a few reaction rates. And also, a problem is that there are many different situations. There are transfer and capture cross-sections, you have resonance, non-resonance. And in heavy nuclei, there is another problem, which is the level density. So this is a field where there is no systematics. If you know one reaction, you don't know a similar reaction. If you compare, for example, lithium 7p alpha and lithium 8p alpha, there is just one neutron difference, but the properties are completely different. So each case is completely specific. This is one of the difficulties, but also one of the attractive things of nuclear astrophysics. So as a theoretician, I want to just briefly show some different theoretical models. One possibility is to use fitting models. And you have here an example of data which have been taken here very recently. This is the lithium-8p alpha cross-section. And this is a fit of the cross-section. So the goal of a fit is to understand the resonance structure, the resonance properties, and also to extrapolate the cross-section down to stellar energies. So stellar energies here are almost zero. There are many cases like this where the data are fitted by some model, and here it's the air matrix theory, which is very popular in this field. Another approach is to use the potential model, and in the potential model you neglect the structure of the colliding nuclei. So the colliding nuclei are represented here by these two spheres, and well, this is a rather simple model. You assume that the Hamiltonian is just a kinetic energy and a potential between the nuclei. You have here an example with the helium-3 alpha gamma reaction, and here you see a typical problem that theorists are facing, which is that in general experimentalists don't agree with each other. So you have different data sets, and you don't know which one is correct. Okay, this is live. And another possible approach, which is more sophisticated but also more complicated, is to use microscopic models. And here one includes the internal structure of the colliding nuclei. So here, instead of having a general potential between the two nuclei, we start from a nucleon-nucleon interaction, which is here this Vij. And of course, the nucleon-nucleon interaction is not exactly known, but we know very well the general properties. So this kind of model has more predictive power, but of course it's almost complicated. And you have here a recent example with the deuteron plus deuteron reaction. And you have here the data, and you have different microscopic calculations with different nucleon-nucleon interactions. The black one is a simple interaction, and the blue and the red curves correspond to realistic nucleon-nucleon force containing tensor interaction. And we shown in that paper that it was very important. Okay, so I'd like to finish my talk with a few words about nuclear physics beyond astrophysics. I showed you the application of nuclear physics in astrophysics, but of course there are many nuclear physics applications which have their own interests. They are not related to astrophysics. And again, I start from the chart of the elements. You have the stable nuclei, which present a large binding energy. And at the opposite, you have what is called beyond the drip lines. The binding energy is negative. The nuclei don't exist. And the blue point corresponds to neutron-rich nuclei, and the red point to proton-rich. So those nuclei do exist, but the binding energy S is very small, and these are consequences on the size of the nucleus. So if you assume that the nucleus is made of a core with A-1 nucleons, and there is one external nucleon which is weakly bound to the core, you start from the simplified Schrödinger equation. And we know that this potential V goes to 0 at large distances. So we know the wave function at large distances, and is related to the binding energy here. So if you use this simplified model to compute the radius, which is an important property of the nucleus, then you immediately see that it's proportional to inverse of the binding energy. So if you have small binding energy, you expect the radius to be very large, and this is called halo nuclei. And there is an example here with lithium-11. So lithium-11 contains 8 neutrons. It's here at the drip line. And you have here a diagram of the different lithium isotopes. Lithium-6, 7, 8, 9, which are stable or almost stable with a large binding energy. And you can see here that the radius is almost constant. And when you switch to lithium-11, the radius is very large, and this is due to the small binding energy. And there is a difference of about 1 Fermi here. So if you compare a picture of lithium-11, which is presented here, the radius is almost as large as lead-208, which contains about 20 times more nucleons. So these are nuclei with very specific properties. There are other examples, helium-6 here, and on the proton-rich side, boron-8, neon-17. And so for experimental application, we need, of course, radioactive beams, and for theory, it's almost more complicated, also more complicated because you need to include this breakup effect. So these nuclei are easily broken up. So you have to include that in the theory. And from to compare with experiment, there are essentially two kinds of experiments. One is elastic scattering, and you have here a recent example of lithium-9 and lithium-11 cross-sections. They are divided by the Coulomb cross-section to remove the Coulomb effects. And you may expect lithium-9 and lithium-11 to be more or less similar. But lithium-11 is very different from lithium-9. And again, this is explained by the halo effect. And another approach is to use breakup reactions, but I don't want to enter into detail. So to deal with this weakly bound nuclei, the main method is to use a continuum discretized coupled channel method, which was introduced for the deuteron, in fact. And well, the standard description in CDCC starts from a two-body or three-body description of the projectile. For example, lithium-9 described as lithium-11 described by lithium-9 core and 2 neutrons. So here in this theory, you need different interactions. You need interaction between core and the neutron, between the neutrons, and between the constituent and the target. So these are the traditional ways to deal with CDCC. And another approach is to consider a many-body description of the projectile. So here you only depend on the nucleon-nucleon interaction inside the projectile, and you also need a nucleon plus target potential, which is rather well known. So this type of method is, of course, more complicated, but probably much more predictive power. And this is something which I'm doing during my stay in collaboration with Maher Hussein. So this is my conclusion. I've tried to show you that astrophysics needs many inputs, and of course not only nuclear physics, but I essentially focused on nuclear physics. And also in nuclear physics, there are many other data. I just spoke about reactions, but there is also a need for beta decays, for masses, for fission barrier, and so on. So there are many data which are necessary. And, well, this field is called nuclear astrophysics, for a contraction of astrophysics and nuclear physics. And, well, the main challenges are that you are dealing with low energies, with radioactive beams. And, well, I mentioned that there are many different cases. And also, I didn't talk about other processes like neutron capture or carbon burning, oxygen burning. But there are many important and interesting reactions in this field. So I think I'm done, and muito obrigado to all of you.
Regarding that idea that the sun is made of a gas providing from oldest stars. Huh? In some way, the distribution of nuclear elements in the sun should be the same distribution of the elements in the explosion of the supernova. The amount of hydrogen and helium, etc., in the explosion of the supernova would be the same that we have in the sun.
Yes, but we don't know the abundance distribution in a supernova.
Okay, but if your sun has born from the gas of the supernova, the distribution of elements in the sun should be the same in the...
Well, similar, yes.
Yeah, and also in the Earth.
In the Earth, okay, maybe. This is well, this I don't know.
I think it's possible to compare the distribution of elements in the Earth and the Sun. Should be the same if they have burned of the same gas.
Yeah, sure.
Except maybe for the light elements.
Well, these distribution abundances are coming from analysis of meteorites. So from meteorites you can get the abundance in some far distance objects.
Yeah. Okay, you said that there are thousands of reactions that we should know the cross-section to make some predictions. But there are already predictions of the evolution of the stars.
Yeah.
This picture can change a lot if one of that cross-sections change a bit or not.
Well, there are some reactions which plays a very important role. For example, C12 alpha gamma. That's, well, because there are many reactions, so it's difficult to extract one which is the most important. So I know that astrophysicists use a large number of reaction rates. But I think only a few of them have a very important contribution.
José Roberto Oliveira. In your estimation of the mass of the galaxy, did you include the dark matter also?
No, I didn't estimate it myself, so I don't know exactly where it comes from. So we know that there are about 10 to the 12 stars in the galaxy. So this, I think this mass of the galaxy comes from a very rough estimate. So 10 to the 12 times the solar mass. I don't think there is dark matter included there.
Se não tem mais perguntas, vamos agradecer o professor Pierre Descouvemont e agradeço também sua presença. Muito obrigado.